So our first presentation will be by Agnieszka Herman from from University of Gdańsk, Poland, and she'll have 1 hour for this, 45 minutes for the presentation and maybe 15 minutes for questions.
Hello everyone, I'm Agnieszka Herman and I'm going to talk about numerical modeling of wave-induced collisions. As you might guess from the way the title is written, collisions between ice floes and structures will be just a very small part of my talk. In the most part I will talk about floe-floe collisions. And before I begin, I would like to thank so many people that I don't even list their names, but the reason for that is that part of what I'm going to talk about today is based on my quite old work from some time ago, but some parts are very fresh, very new, and they were certainly inspired by countless discussions and chats during this CIS program here since August, so I'm really very grateful to all those persons with whom I interacted. The plan is as follows. I will start with some introduction by showing you some pictures and movies of colliding ice floes in very different conditions, just to remind you of different types of situations in which we may find collisions between ice floes. Then I will describe the model, and in the remaining part of my talk I will show you some selected aspects of the modeling results, which are either interesting. I think what I'm going to talk about will be a very simple model, in fact, but nevertheless it produces some very interesting behavior in some for some ranges of parameters. And also I will try to show you those aspects of the results that might be important. Flow collisions may be important for many different reasons. Of course, one reason is are forces on structures in wave and ice field. Other reason is relevant at much larger scales. Here I mean scales that are large compared to the period and length of a typical wave, and also larger than individual ice floes, namely I mean processes related to, for example, stress in the ice due to colliding ice floes. And when we think about wave-induced collisions between ice floes, we of course naturally think about the marginal ice zone, which sort of by definition is influenced by waves. Flow collisions are of course a tiny part of a whole range of interactions between waves and ice, interactions that also include other processes, dynamic and thermodynamic processes. And it is quite obvious to say that the nature of collisions will depend on the properties of the waves and on the properties of the ice, like ice thickness or the size of ice floes. And also it depends on what is in between ice floes, in the sense that we may have just water, or in freezing conditions we may have a dense mixture of water with radial crystals. And it seems understandable that we would expect for flow wave interactions and for flow wave collisions to be affected by the fact that water has viscosity due to those higher viscosity due to the presence of those crystals. What is also interesting is formation of patterns of ice floes on the sea surface, in which we assume that waves play some role. We don't really fully understand how those patterns emerge and how they are formed. Some of them can be reproduced with the model that I'm using, some others not really. So just some examples. This is a video very similar to the one you have seen this week already at least once, maybe more times. This one I've got from Mike Collins from the Naval Research Lab. He took it in the Beaufort Sea in October 2016, last year. And these are pancakes moving on waves, probably very young pancakes that are small. What is important from the point of view of what I'm talking about now is that the size of the pancakes is at least 2 orders of magnitude smaller than the wavelength. So these are small objects moving on waves. And what you could see, there was a zoomed part of the movie. The pancakes are colliding. Maybe the word collision does not really seem very appropriate in this case, because the velocity of neighboring pancakes is usually very similar, so they doesn't want to run once more for some reason. Anyway, so this is a case where the collisions do occur. We have periodic divergence and convergence on the sea surface related to the wave motion, and we have the according convergence and divergence of the pancakes. The next example is a very different one. These are thick ice floes at high ice concentration, and here unfortunately the camera was quite low about the ice surface, so it's not really very easy to see the actual collisions, but when you look closely, they are there. I don't know what is going on. And we can also see overwash. In this case, the floes are large, and the velocities between colliding floes are very different. So we had a rapid collision and often overwash on the ice surface. And here, the amplitude of the horizontal displacement of ice floes is not very large because there is no space for that, but still the accelerations can be very high over very short periods of times when the ice floes collide. And the last example is from the laboratory, from HSVA. Again, we have seen many photos from HSVA this week. I will tell a few sentences about this project later, but here are just 2 examples, one after the other, of colliding ice floes. In the first example, the ice was broken by waves, so we have irregular shapes of ice floes. The next one that you will see is with square ice floes, very regular, that were cut manually. But what is more important is that in the first example, the ice was allowed to drift towards the open water area in front of the wave maker, so the ice concentration was lower. There were larger spaces between floes. In this case, the ice edge was kept in place, so the ice concentration was approximately 100% all the time. And this I don't know what is going on. This produces a very different pattern of collisions. I hope you can see it once more, but for some reason I can't make it around. In this first case, we have, when we follow one selected ice floe, then there are periods where nothing really happens. It just moves without colliding with neighbors. And then there are periods where collisions are quite frequent, and those regions of more frequent collisions move across the ice sheet due to a simple fact that locally we have higher energy in these regions of higher local ice concentration, and then the flows tend to move away from that region, and the zone of collisions also moves across the ice. In the second case, the ice concentration was so high that, in fact, I'm not sure if we can talk about collisions anymore, because the within each wave period, the time during which the flow had contact with its neighbor was not very short, it was substantial. In some cases that we observed, it was like 3/3 of the wave period. So in fact, most of the time the flow was either pushing the flow in front of it or was being pushed by the flow behind it. So these are not instantaneous collisions anymore. This is something very different. And my goal was to have a model that would be able to reproduce these different aspects of collisions, different types of conditions in which we have collisions, and on the other hand, I wanted the model to be as simple as possible, so to capture the basic processes that were going on. And I'm using the model that I've been developing during the last couple of years, which can be applied to many different things. It is a bonded particle DEM, and it is being used not only by me now, but also by other people. The code is freely available, so if you are interested, you might look into that paper. In this case, it is applied in a very simplified setting. These are the assumptions. What I model are only horizontal motions of ice flow, so it is a model of surge motion. And in vertical, we simply assume that all the time the ice is in Archimedean balance. This allows us to simply calculate the submerged surface area and volume to estimate the forces acting on the ice. And in most cases, I used round flows in order to compare the results with this lab test that you have just seen. I used square ones. What is a very important assumption is that the waves are prescribed. They don't have to be regular deep water waves. We may prescribe something else just as well. These are simply the waves that I used in the simulations that I'm going to talk about today, but the most important thing is that they are not affected by the ice, so this is definitely a limitation, at least in some situations. And all those assumptions make the model very similar to the previous ones. This is a rather arbitrary list of references. But there is one difference, and as I'm going to show you later, it's an important difference, namely that the forcing acting on the ice floes is not calculated in the center of the flow. It's integrated over the surface area or volume. It depends on what kind of force we are considering, and it makes the model applicable to a much wider range of flow sizes than those that are valid only for very small ice flows. So what we are solving, as in every DEM, we have heard a lot about how DEMs work today earlier, so I won't repeat that. We solve n momentum equations for n ice floes, and in the computations that I'm going to talk about today, we have 4 forces acting on the ice. The force from the incident waves, the added or virtual mass force, the drag force between the ice and water, and crucially, if we want to simulate collisions, we have to have the contact force between ice floes, which is for any given flow, it is a sum of contact forces from neighbors. And I'm not going to talk more about the added mass in all simulations that I did. I used a very small value of the added mass, but in fact, the same things that I'm going to say within the next 5 minutes are valid for the added mass force as well, namely that it's not flow size independent. It should be calculated differently for large and small ice floes. So the force from the incoming waves is calculated by definition, so to say, by integrating the dynamic pressure over the wetted submerged surface of the ice floes. And when we use the pressure from the linear wave theory and do the integration, we obtain a very nice formula, nice in the sense that DEMs were like this kind of formulas that can be evaluated based on variables in the middle of the flow. So it makes everything very simple from the practical point of view. And the force is almost identical to that used in slope sliding or similar simple models. But we have this correction factor here, which is a function of Kr. K is the wave number, R is the size of the flow. We may have flows of different shapes, and the form of this function is different. So here are 2 examples for circular ice flows and for square ice flows. And the overall shape of this function is that we have values close to 1 for Kr close to 0. So this reduces this formula to the one valid for small objects moving on waves. And when we increase the flow size or decrease the wavelength, we obtain lower values. And the same is true for the drag force. In general, it is a sum of skin drag and form drag. In all my calculations, I used objects that were flat, so their horizontal dimensions were much larger than the ice thickness, and I used only a skin drag, but it can be easily extended to form drag as well. But what we have to do is to integrate the local differences between velocity of ice and water over the lower surface of the ice. Here we have 2 components of this force in the x direction, which is, I didn't say it, but this is the wave propagation direction. So in the perpendicular direction, this formula is very simple. In the x direction, it is simple as well, in the sense that it is easy to write equations to calculate it, but these equations are not really very nice to solve for each ice flows at each time step, because of course what we have to do is to find the points where the relative velocity between water and ice is 0. And not only the positions, but also distances between those points, of course, change constantly. And then we have to integrate over those fragments of the ice floes and add everything. So the equations are quite simple. I won't go into detail, but we first have to find those points, and then we have to integrate this formula that we had 2 slides ago. And this is relatively simple for a square flow. If it is circular, it's even longer. So that's why instead of this exact formula, I used a approximate one. This is how it works. Some examples. What you see here is time on the vertical axis, scaled with the wave period, so it goes from 0 to 1, and there is the flow velocity on the horizontal axis. So most of the time, again, it is scaled with the wave amplitude and frequency. Most of the time we move within this region between minus and plus 1. But not always, because after collisions for short time periods the velocity can be very high, so we are sometimes thrown farther to left or right. In any case, here we have this integral drag force evaluated for 4 selected relative flow sizes, and this is how simple models do this based on the wave phase in the center of the flow. So what we see is that for large ice flows, in this way, when we use this formula, we don't take into account this effect that large ice flows are much less sensitive to the phase of the wave than the small ones. And I won't spend more time on this, but I found some simple weighted average expression that produces not exactly what it should, but it's very fast and very simple. And again, it has this nice form that it just depends on the phase of the wave and some correction factor. And I'm spending so much time on that because it seems like a small detail, but in fact it produces a very different result of the model. So even if the drag coefficient is very low, for relatively large ice flows, we have this sensitivity to how we calculate the drag, and then we have a different collision pattern, different stress in the ice, and so on. So it's not a very small and irrelevant detail. And the final thing, this is this last term in our momentum equations, is how we handle collisions. Again, without going into much detail, basically there are 2 groups of methods to deal with collisions. In the first one, which was used in molecular dynamic models and models similar to those, this first method is based on so-called event-driven algorithm, so which means that our model progresses in time from event to event, and the event is a collision. So what we have to build are event queues storing the information about partners and times of collisions. And this seems quite simple. Sometimes it is simple, usually not. It is suitable, especially in the case of situations when the presence of particles or grains does not affect the motion of the surrounding fluid. But it is suitable only for very short-lived collisions because the underlying assumption is that the collision is infinitely short. So we in fact do not include the contact force in our momentum equations. We simply detect when the collision takes place, and we update velocities at this time instance according to a certain rule. And those early models of ice flow collisions by Haley Shen and Steve Ackley and so on were based on this type of approach. And the second method is, I don't like this name, time-driven. It's strange, but anyway, it is a method based on a constant time step. in which we do calculate the contact force based on so-called overlap between particles, which is in fact the formation of the particle, not the overlap. This is how most DEMs do this, and in this case we have to use a certain contact model, and we have to specify expressions describing the normal and tangential component of the force. Here for flow collisions, what is important is this term depending on the relative velocity between colliding ice flows, which is a function of the restitution coefficient. So just before we look at some results, it is worthwhile to take a look at how the equations really look. Here we have the velocity scaled with a omega, amplitude and frequency of the wave, and we have a forcing term with some factor which is smaller than 1. We have the nonlinear drag term and the contact force, which again depends on what kind of contact model we use, and in the direction perpendicular to the wave propagation direction, the contact force is the only source of the motion, and we have the damping, which is a very simple expression. So the set of relevant parameters is ice concentration. Of course, it does not occur explicitly in the equations, but we have a certain domain and a certain number of ice flows within it. Wave steepness, the relative size of the flows. Here I grouped those two parameters together because we have their ratio just in this equations, and the restitution coefficient plus some other material properties depending on the contact model that we are using. And finally, just a few words about the structure. If we have them in our model, in this case, this is just a discrete element or a group of discrete elements. It doesn't have to be one, with additional force acting on it, and this force has two components. So the first one is proportional to the displacement of the structure from its initial position with some constant, and we have a damping term. So again, this is kind of a standard way to do this, although the model in general also allows to have simply walls, rigid walls in the domain. So we may specify a structure also in this way. And the first question when we want to apply the model, of course, is what is the range of flow sizes in which we can use this? And in this case, we don't take into account any interactions between the ice flows and waves, so we don't have diffraction effect and so on. What you see here is in the background is the figure from the paper by Lucas Yu, showing experimental data, and it's not easy to see, but there are two curves in this original figure. This one is showing the results of the slope sliding model, and as we see, it is not sensitive to the size of the ice flows, and there is a black continuous line which passes through the data points very well. It is the result of the potential flow model, and I added 3 curves on top of that, showing the results of the present model for 3 different values of the drag coefficients. As you can see, there is not very much sensitivity to drag, but only in situations without collisions. So this does not mean that the drag is not important. And for very small ice flows, this curve goes to 1. This is how the model is constructed, because it's it produces, for very small ice floes, it produces motion exactly following the wave motion. And now back to that experiment at HSVA that I mentioned in the beginning, showing you those video. This was done within a project called LS-WISE, which is an abbreviation from load on structures and waves in ice. And the project consisted of many parts. I was responsible for the part related to ice breaking by waves, which has nothing to do with what I'm going to talk right now. There was a part related to a wave interaction with a structure, and all credit for that goes to Andrei Tsarov and Sergei Sukhorukov, who I'm not sure if he is still there, but he was there this week. And you can see the setup here. We have a structure and ice floes cut into regular pieces, and we run waves with different parameters through that. And one of the aspects of the results is shown here. We have the Ka, so wave steepness on the horizontal axis, and the vertical axis shows the ratio of the amplitude of motion of that flow that was closest to the structure. It's the ratio of the horizontal to vertical amplitude measured at the flow. And yeah, the results are like this. Most data points, they are not very many, but they sort of seem to align along a straight line. There are those 3 points that are very far from that. And when we look at the time series of the flow acceleration from all those cases, I know these are not very nice plots to look at, but the 3 time series that are shown in red correspond to those 3 points that are high above all the remaining ones. And I don't know if you see it, maybe it requires some more time for watching this figure, but these are the 3 cases with most frequent and most regular collisions. And this is not just an impression. When we plot again the same variable against the number of collisions per wave periods, these are those 3 points from this upper figure. So this suggests that the pattern of collisions is sometimes somehow not the same, and that is that this pattern very strongly influences the horizontal motion of that ice flow. When I started to run a model for this case, trying to replicate what was going on, actually there were not very many parameters to play with, because the flow sizes and the wave characteristics were given, and I thought that the ice concentration was given as well. It turned out that it was not so simple, because at the ice edge we had like a boom which did not behave in a very nice way. It sometimes tended to move a bit, and it seems that it was enough to change the distances between the ice flows in a way that it affected very strongly how frequent the collisions were. So the model results that you can see at the bottom are from 2 sets of model runs obtained for 2 almost identical but slightly different ice concentrations. And it was enough to shift the amplitude of the horizontal response for between roughly 0.5 to close to 1. And I don't know enough about ice structure interaction to say if it's significant, important for anything or not. If it's important for a structure, from the point of view of a structure, if the collisions are so frequent that the effects of collisions do not die out before the next collision happens, or if they are less frequent and we have a pattern like this. What you see here are the forces measured on the structure. So maybe it's nothing very relevant, but in any case, this result also showed that the amplitude of the forces that are produced by the model are similar to those that we observed in this case, at least. Compared to the force amplitude due to waves alone, it was between 10 and 30 times larger. And now I would like to show you just some examples of how the time series of flow velocities and forces may look like. I won't go into detail, there's no time for that, but it is just to show you that this pattern might be very different. This is a case with relatively low ice concentration and small ice flows, where we have this effect of propagating collision zones across the ice sheet. So there are time periods where nothing is really happening, the flow is moving without collisions. There are periods of frequent collisions. When we compare this to measurement from that case that you could see in the video, this is of course not exactly the same as in the model, but still we can see those periods without and with collisions. Here another example, at higher ice concentrations, this always produces more regular free collision patterns. So we may have frequent collisions during a certain phase of the wave, like in this case. And what is interesting and I think important is the role of the friction coefficient or drag coefficient. Here are modeling results obtained with everything equal except the value of the drag coefficient, and each plot is constructed the same way. We have flow velocity on the horizontal axis, and on the vertical axis there is the wave force, the drag force, and the contact force. And these are just over 1 million points from different ice flows and different over 120 wave periods. So when we look at the case when the drag is very low, we see that our data points are scattered all over the place. When the drag coefficient is very high, what we obtain is a very repeatable response of the model to the forcing. So the drag regularizes the response, so to say. And the last example, this time for large ice flow. So you see that the amplitude of motion is quite small compared to the amplitude of the wave motion. And when we again compare this to some measurements, this is an example of a similar situation from this case of square floats packed densely together. And when you take a look at the time series of forces, here the yellow curve is the drag force, the violet curve is the contact force. You can see that both of them have very high amplitude, very high compared to the amplitude of the wave force over extended periods of time. So these are not spikes anymore, like it was the case previously, but after each collision we have this time period where the flow is pushing the other one in front of it, so that the contact force is very high, and in response the drag force is high as well. This is a very different case from those short-lived collisions previously. It's the results are very regular, actually, even if we introduce some variability of flow sizes to the model or any other parameters. Here is an example of modeling results with very wide flow size distribution. So we had some mean flow radius, and what you see in the pictures this time are results for just 4 selected ice floes with very different sizes. So we have a very small one, which is in blue, and the largest one is violet. I don't know if it's important for anything, but I really like those different curves that are very different for different model configurations. So it's not something that repeats itself all the time. It's really it repeats itself over many wave periods when we run the model for a long time with the same parameters, but it's very different. It's probably just a curiosity and produces nice pictures, but it is also responsible for covariance between velocities and forces, and towards the very end I'm going to mention why this might be important. When we move to 3D from 1D cases, of course we have collisions in all possible directions in terms of forces and orientation of contact planes, and I think it's quite clear that when the ice concentration increases, then the amplitude of velocities and also collisional forces increase in this perpendicular direction. So the situations with low ice concentration are close to one-dimensional ones, and when we increase the ice concentration, then the velocities and also the amplitudes of motion and so on increase, which has consequences for stress in the ice. And this leads us to this final part of my talk, in which I mentioned larger scale effects of collisions. And this is related to something Evgeny Aksenov talked about in his talk, the granular temperature and the equations that describe the time evolution of granular temperature, which is simply the kinetic energy of the fluctuating part of the motion of ice floes. And what is relevant for here is are those two terms to the right of this equation. This gamma term describes the rate of dissipation of the granular temperature, and it basically consists of two parts. One are inelastic collisions, the other one is friction between ice floes, and the last term is in fact the sum of many terms which describe the rate of work which is done by body forces acting on the ice. So the forcing from the atmosphere or the ocean is in here, and forcing from the waves is going to be here as well. But the important is the form of this term, that is the forcing multiplied by velocity. So what we are interested in is if there is a covariance between the fluctuating part of the velocity and forcing, because if there is, then it contributes to the granular temperature. And originally, when we look into the paper by Gianni Felfan, this framework was applied to analyze how the shear in ice changes with the distance from the ice edge when we move deeper and deeper into the marginal ice zone. So how the velocity of the ice, which is in the direction parallel to the ice edge, changes when we move in the direction farther from the ice edge. And the assumptions that were made were consistent with this application of the granular temperature theory. So the assumption, one of the assumptions was that on longer timescales, the turbulent fluctuations within the ice are balanced predominantly by friction between ice floes. And one of the implications was that the collision-related part was only related to the velocity gradients across the marginal ice zone, which is definitely not the case that we are discussing right now. Here we have something closer to this situation when we reach the stationary state, and we may think of spatially uniform conditions with certain wave field. Then we have probably, in most cases, the collisional term larger than the frictional one, at least at ice concentration which are not so high that the flow really shear one on the other. And this is balanced by this forcing term. So from this point of view, it is interesting to look at the modeling results in terms of how high the granular temperature is and what is the covariance between the fluctuating velocity and forces acting on the ice floe. So we may take separately the wave-induced force, the drag force, and the collisional part of the force. And when we look at the granular temperature, it's not very surprising that it is comparable to the squared velocity associated to the wave motion, of course. So it's the same order of magnitude. And this covariance can be very small or very large, depending on two things, basically: the restitution coefficient and the drag between ice floes. So when we compare two cases with zero drag and very high drag coefficient, in the case of zero drag, the wave for this term related to wave forcing is balanced by the terms related to the collisional part, clearly, because we prescribed that the drag is very small. And in the other case, we have larger contribution from the drag, and which is a problem because we usually don't know what this drag coefficient really is. And similarly, I think this is the last slide. When we look at stress in 2D cases, stress defined as a sum of two terms, one related to kinetic energy, the other to the contribution of contact forces, we observe very similar patterns in all cases, just the values are different. Namely, that when we increase the ice concentration, what we observe is a gradual increase of the stress component in the sigma xx in the x direction, with a very rapid increase when the ice concentration reaches a certain threshold. And in the perpendicular direction, first the stress is usually zero. We almost have no collisions in the direction perpendicular to the wave propagation direction, and then the values get larger. And in most cases that I analyze the at large ice concentration, the stress component is like between 60 and 80% of this one. So this is not a very small value. It's comparable. So the case is not one-dimensional anymore. And the values, of course, I won't describe it in detail anymore, but they again depend very strongly on those two things. So these are the conclusions. I think I won't read them out instead, so you can ask questions.
Questions?
So in the tests, in the experimental tests,
Yeah.
the lab tests you showed, the waves looked very mild, and the maximum Ka value, the steepness seemed to be about 0.05,
Yeah.
which confirms that. And then in the results you were showing later, you're going up to 0.2, which are energetic waves. I think
Yeah.
they're 0.2.
Yeah.
But do you think that the same physics that's built into the
I'm
model is
not
valid?
sure that.
I mean, I'm thinking
Yeah.
about rafting from
Yeah.
my experience of these tests. There are other things in there. Did you? I guess my.
I mean,
it's really a question. But I guess my question is: did you run with more energetic waves in the lab experiments?
No, I didn't have any data within this range of wave steepnesses to compare the modeling results. So that's true. It might be beyond the range in which the model results are valid.
Next question?
If let's say, if you would run simulations of such model that we have like edge of broken ice and waves are coming from open water on the edge of broken ice, and ice is not confined, so then flow collision will initiate increase of distance between flows. And what do you think? How quick flows stop to collide?
I have not analyzed the whole range of different conditions that, but I did run the model in the situation which you are talking about, and it's a very fast response actually. So
Very fast.
yeah, I mean fast in terms of the number of wave periods that you need to.
Yeah.
So. But it is partly balanced by the drift of ice flows with the waves. So at a certain stage, at least what I observed in those model runs, the drift of ice flows back from the ice edge did not continue infinitely, but at some point you had some.
But you probably have some like strip inside ice where collisions are most intense, and since the wave penetrates deeper, so that this region will also move.
The model produces stripes of ice flows in many different configurations. Even when you will start with a confined or periodic domain, it tends, especially when the restitution coefficient is low, because it makes it easier for the flows to stay together. It produces stripes parallel to wave crest, so perpendicular to wave direction.
So it would seem in nature that when you have a flow generated, it originally had a through thickness temperature gradient, and then in time that temperature gradient is changing because it's now exposed to water around freezing around its perimeter. So its temperature gradient and therefore mechanical properties, especially around the perimeter, and presumably the coefficient of restitution, so the energy involved in a collision will be a function of time after formation. Is that on your radar screen at all to deal with that sort of thing?
I didn't do any simulations that would take into account those thermodynamic effects. The same thing is with what I mentioned in the very beginning, that if you have phrasal in water, then the effective restitution coefficient is very, very different from the one in clear water. So you have to sort of know the way how to specify your restitution coefficient as a function of variables that are
all those parameters. Okay,
Yeah.
thank you.
Hi, Agnieszka. You probably said this, but I didn't pick it up. In your experiments, was there any observed sliding between the flows, frictional sliding between the
You
flows?
mean the lab experiment?
Yeah, the lab experiment.
We didn't see
Just saw them
anything.
touch
Although
it.
when you look at the time series of vertical accelerations, you see some peaks at collisions, but those peaks are, as far as I remember, like 10 times smaller in amplitude than in horizontal acceleration.
Your model allows sliding, right?
It doesn't.
Doesn't allow
It
sliding.
doesn't.
Not even with the square flows. Wrong. Okay.
In the comparisons with the lab tests, I assumed that the situation was one-dimensional. So, and it was expected in two cases when we observed some rearrangement of the positions of the flows, but I didn't include those two cases in this.
One more question.
Yeah. You've gone so far with this. Is it possible to model the two-way coupling and the wave attenuation?
In this version of the model, no.
Is it
In
possible?
this version, the only thing what you can do is to prescribe how, I don't know, wave amplitude changes across your model domain, which has nothing to do with coupling, of course. So in this version of the model, no.
I'm just wondering what your opinion is. How hard is it to do that?
I mean,
It's okay.
it's because the question how hard is contains a lot of different aspects of the thing. It's certainly hard computationally in the sense that to run the couple model requires much more computational power than to run this kind of model. I did recently some simulations in 2 dimensions with one horizontal, one vertical dimension, and in those the waves were coupled to the ice motion, but it's not this case.
Okay, I think we should stop here. Thanks again.